So today we are going to be summarizing vector fields and generally going over some of the most important theorems and concepts in Calc 3. So beginning with parametric functions, or also known as vector-valued functions, where we are taking a vector and that vector moves us from a one-dimensional region to a multi-dimensional region. So beginning with derivatives, what happens when we differentiate parametric or vector-valued functions? Well, really, we solve this by differentiating each component function. And this is giving us the change in x or the change in y or whatever variable we're using respective to each component. So when we differentiate once, the result is going to be the velocity tangent vector, and differentiating twice is the acceleration tangent vector. The acceleration tangent vector, it is important to note, can also be represented by adding the tangential component of acceleration and the normal component of acceleration. So the tangential component of acceleration is solved by dotting the velocity with acceleration, so basically the first derivative with the second, and then dividing by the magnitude of the velocity, also known as the magnitude of the first derivative. This component is going to demonstrate the acceleration of the particle without being influenced by the direction. So geometrically, this is going to look like a standard tangent vector, similar to the velocity tangent vector. Now, the normal component of acceleration, I have how it is calculated up on the screen. The normal component of acceleration is going to point in the direction the function is turning in, this component does not consider the acceleration or the speed of the function, it just demonstrates direction. And when we combine these two, which we do by adding them, this is going to result in the acceleration tangent vector. So that is considering both the speed or the acceleration and the direction and how they're influencing each other. So it's going to be geometrically represented by, we know that the tangent vector and the normal vector have about a 90-degree angle between them. And so the acceleration tangent vector is going to be somewhere in between that, depending on how these two are influencing each other. And overall, it's going to calculate the total acceleration and predict the direction of the graph. So this is important because these two vectors can give us information that allow us to make predictions about the function. For example, the velocity tangent vector, which is going to appear as a line matching the graph around the point solved, for like a standard tangent line would be to a normal function, and it's demonstrating the speed and the direction of the particle at that moment. So we know things like if the line is steep, then the particle is going to move quickly, whereas if the line's slope is gentle, then the particle is moving more slowly. The direction is also going to give us the direction which the particle is moving along the function. We're looking for things like, does it increase moving left to right? If so, the particle on the function is going to move up on the function as it travels from left to right. Additionally, the acceleration tangent vector, which is going to appear again as a line pointing some direction off of the function, so it's not a tangent. When you combine both the tangent and the normal, you get something in between. And the starting point is always going to be the point that we are solving for, that we are plugging into the equation. And this is going to represent the rate at which the velocity changes and the direction that the particle is turning, which is some pretty important information if you're looking at something, say, a car moving on a racetrack. Again, I already stated this before, the tangential component versus the normal component, which are appearing at a 90-degree angle. Now let's talk about integrals. So when integrating a vector-valued or parametric function, we are integrating component by component, similar to how we differentiate, and the common practice is to put it into our IJK form. Integrating takes you from acceleration to velocity, and then if we integrate again, we can go from velocity to position. Integrating is always going to result in a plus c, but the difference between this plus c and what we're seeing in Calc 1 and Calc 2 is that RC is now equal to c1 of the I vector plus c2 of the j vector plus c3 of the k vector. So c is not just some arbitrary constant, it is an arbitrary constant vector, which is an important distinction. A practical use for integration of vector-valued functions is to determine things like the direction or the speed or the total distance traveled or even just the position of the function, and we always start out with some information about the function. So we can determine position if given an initial position and the acceleration of the function or the velocity of function by simply integrating and plugging in the initial position and velocity values. We can determine the speed of the function by taking the magnitude of the velocity of the function. And we can even graph the original parametric function if we're given both of the initial position and velocity information, as well as the acceleration, or more simply, if we're only going from velocity to position, then we only need the initial position information. Now let's talk about some multivariable functions, which are functions where we are going from multiple dimensions back down into one dimension. So when we're differentiating, we are generally taking the partial derivatives, and that is taking the derivative with respect to one of the multiple variables present. So we're going to do this by holding the other variables in terms constant, and then we are differentiating with respect to just that one variable. And the notation is slightly different, and it's written here as the partial with respect to f divided by the partial with respect to whichever variable we are differentiating by. The partial derivative of the function with respect to a variable is going to determine the rate of change in the direction of that variable. So say we're using x as our variable, then the partial with respect to x is going to calculate the rate of change, which is also the slope of the tangent line as seen geometrically, in the x direction, which basically just means how the function changes as we move in that direction. If we're visualizing a multivariable graph, it is in 3 dimensions at least, so it could be in more dimensions, and it's the partial derivatives with respect to a variable determines the same information as a tangent would, only it describes the information only passing in one direction, and there's infinitely many directions as the graph approaches a point because, again, it is in multiple dimensions, it's in 3 dimensions, it's covering a surface. Commonly, we use a disk when we are going to talk about that more in integrating. So partial derivatives can be expanded into second and third and so on derivatives. We simply apply the same principle, which is holding the variable we're not dealing with, not integrating by, not differentiating by, as constants. The second derivative with the same variable, which is going to be the can be represented as f subscript x, expands on the information of the first derivative, giving information about how that first derivative is changing, like the rate of change, whether it's increasing, etc. We're not going to talk about this now, but the discriminant, which uses second derivatives as well as mixed partial derivatives to determine things like concavity, if a point is a maximum or a minimum, or if it is a saddle point. And now we're going to move on to this concept about a mixed partial derivative. So what is that? Well, a mixed partial derivative basically means that you're differentiating with respect to a different variable than you did with a first derivative. So, for example, say you differentiate with respect to x, and then you differentiate with respect to y. X and y aren't the same variable. You're differentiating with respect to 2 different variables, and that is going to be a mixed partial derivative. The result is that we're learning more information about the first derivative in the direction of the other variable. Now, for certain equations that don't have anything in terms of x and y, say it's like x squared plus y squared, there's no term that has x and y. So those mixed partial derivatives are going to be 0 because differentiating f and with respect to x and then y is going to be 2x differentiated with respect to y, that's a constant, which is 0. And by Clairaut's theorem, we have that mixed partial derivatives are equal if the function is defined on an open disk, containing the point, obviously, and both of the mixed partial derivatives are continuous over the region. So the concept of partial derivatives can be expanded farther into directional derivatives using vector-valued functions. In this case, we're describing a direction as a unit vector, starting from the point we are differentiating at and going in some other direction, and we are doing this so that we can see how the graph changes in that direction. And the goal is to determine how much the derivative acts in the direction of our other vector, and that is going to be calculated by the dot product. That should have sounded familiar. So the directional derivative is basically the dot product of the derivative of the function and the direction vector. Geometrically and visually, this is best explained and would appear as the projection or the shadow of the function onto the vector representing our direction. Another important thing to note for differentiating is also the gradient. So gradients represent a simpler way of formatting the derivative of a multivariable function by putting it into component form. So the gradient is going to be a vector where the components are represented as the partial derivative of the function in the variable it is describing. So that basically boils down to just fx, so the partial of f with respect to x would become the I component, and the partial with respect to y would become the j component, and if there's z or another variable, that would become the k component, and so on. Geometrically, the gradient is going to represent our elevation of our graph, and that just basically means it represents the levels of steepness at each point on the function. The gradient is always going to point in the steepest direction. The fastest way to gain elevation, a way to visualize this would be if you're climbing a mountain and the steepest path is going to be the direction that the gradient points in. If we expand this to 3D, each point on the gradient would represent a different elevation on the map, and this is really seen through topographical maps, which has a variety of different things called contour lines, and each line represents a different elevation, and it's drawn over the location of that elevation, which is a two-dimensional version of the three-dimensional surface. Now let's talk about integrating over multivariable functions. So we use multiple integrals in order to integrate, and we calculate this pretty much the same way that we do with partial derivatives. The idea is the same, that we hold one variable constant and we integrate the one variable that we are integrating over at a time. And there will be the same amount of integrals as there are variables. Now, it's important to note that we are going to be, since it's a multivariable graph, that we are approaching this point from all directions. We are approaching this region from all directions, so bounds are needed to represent all of the variable directions. Integrals can also be calculated in any order of integration. For, say, two variables, we have either dy dx or dx dy. Either way, it doesn't matter, but usually one way is easier than the other. Sticking with two-dimensional regions, or double integrals, we have two types of regions. Type 1 is dy dx, and type 2 is described as dx dy. And that's just a different way of describing these two regions. And again, the concept is going to follow the same thing as the Riemann sum for one integral, only the area of the rectangle is now base times height, and we are using a double Riemann sum as two variables are changing, and so that's how we can represent the change in both variables. The base is going to be the x value of the point, and the height is going to be the y value of the point. The function value is going to be like the area for the double Riemann sum, and subdivisions, and it follows the same concept for integrating. As subdivisions increase, the size of each division approaches 0 as we approach infinity, and if we're integrating assuming that we're going to infinity, then we are able to just simply solve via an integral. Integrating a double integral over a function value of 1 is the same thing as the area of the object over the region, and that is why we represent our dy dx or dx dy as dA more generally. So the double integral is going to find the total surface area of the function over the region described by the bounds. And a double integral can be solved as an iterated integral, so you're basically calculating the interior integral and then you're using that as the integrating region for the exterior integral. And the first set of bounds may be in terms of the second variable. For example, here we are integrating with dy first. C or d could be in terms of x because we are then going to integrate x. You must be integrating with that other variable in the future or in the next integral in order to use it. Three variables follows the same concept but extended by one more. Triple integrals are used. It is the same Riemann sum concept, only a third Riemann sum is taken. They can be represented in any order of integration again. They do represent the volume of the object or the solid described by the bounds, especially when integrating over a value of 1, and their integrating variables is generally represented with dv. 3 variables, again, can be represented by other equations. So say we're doing z equals something is the z bounds. Those z bounds can include x and y if we are integrating next with x and y. Again, they can also be calculated via iterated integrals. And triple integrals will geometrically represent the volume of the function or the volume between two functions. It depends on the bounds and what we're solving for. And also, if these integrals work if they are continuous over the region, but according to Fubini's theorem, they also apply if they are only discontinuous on a finite number of regions. And the average value over the region, whether that's a double integral or a triple integral, is found by multiplying 1 over the integrand, which is going to be an integral with the function value of 1, and then either dA or dV, depending on if it's a double or triple integral, and then multiplied by the double or triple integral over the region with the bounds. And this can also be turned into polar or spherical coordinates. When we do that, we do change dA and dV into either r dr d theta or rho squared sine phi d rho d phi d theta. So that's another important note. So now we are going to be talking about vector fields, where vector field f is going to go from a multivariable region into another multivariable region. So starting with derivatives again, we are again using functions that are vector valued and multivariable. So each component has multiple variables. Starting with the divergence, which is a type of derivative, it represents the net amount of something, like say a fluid or wind current, passing through this multivariable vector field that we have represented as f. The divergence is a derivative, and it is calculated as, it's a type of derivative, calculated as the sum of the partial derivatives of the components with respect to the component that they are representing. P is generally associated with x, q to y, etc. So it's going to be partial p over partial x plus partial q over partial y, etc., etc. And the divergence notation is div of f. So the divergence, again, it calculates the net amount of something considering the directional derivatives, so the derivatives in all directions, and utilizing them by creating a linear combination, which is a fancy way of saying adding them together. If the divergence is positive, it means that there are more things flowing through the region that are going out than they are in. So if we think about this as a water current, there is less water going in than there is going out, or say a faucet is dripping, but the drain is draining it faster. And this can be visually represented as either a larger arrows, so larger would be representing a greater matter, and again we're using arrows because it's a multivariable vector, moving in the outward direction, or if we are seeing a graph that's moving from left to right or another direction, it's going to be in the positive direction, compared to the arrows on the other side or the center. If the divergence is negative, it's just the opposite. It means that more things are flowing into the field than out. So our sink would be filling up with water because the faucet is dripping faster than the drain can drain it. And next we're going to talk about the curl. So the curl of a vector field represents its tendency and the direction that it rotates. The curl is also a linear combination of partial derivatives, but each component is calculated by subtracting one partial from another, where neither partial contains the component of the original multivariable vector field, and neither is calculated with respect to that vector field, and again, neither is going to be with respect to its own variable component. So r is associated with z, so r is never going to be calculated with z, and r is not going to be present in the k component. So that is very difficult to verbally explain. I have an example here on the screen about visualizing it being in a circle and going around the circle and using that to determine what comes next. I'm not going to go into that now. It's a bit complex and difficult to follow without an image of an example. So I will leave that up on the screen. So the curl of a two-dimensional vector field is going to be a scalar, whereas the curl of a three-dimensional vector field is another vector field. And again, the curl vectors is always going to point in the axis of rotation. And then we use the right-hand rule to determine the direction that it is turning. And then again, here I have a description of the right-hand rule, which I won't get into, but it is on the screen if you'd like to see it. It's also important to note that if the curl is 0, that means that the gradient field is conservative. And now we're going to talk about gradient fields or conservative fields, which are basically fields where a function, if you take the gradient of that function, the resulting function is a vector field. So this follows the same concept of potential functions with integration. As with potential functions from Calc 1, they're only unique by constants, which can be adjusted to get another potential function. So, for example, when we take the antiderivative of f, since constants are eliminated by differentiation, when we integrate, we don't know what arbitrary constant was originally there. So this follows the same concept that there are these arbitrary constants, that are all linking these different derivatives to each other and these different potential functions. So this is visually seen as del f is equal to the vector field f, where del f is going to be perpendicular to the level curves of f, and it always points in the steepest direction. Basically, f is the integral of, or the antiderivative of, the vector field f, as the derivative / gradient of f is equal to f. So if we take the derivative of little f, we get big F, and therefore if we integrate big F, then we get little f. So most vector fields are not conservative or gradient vector fields, and there's a variety of tests. Not going into that too much, but an example is that all conservative and gradient vector fields follow the cross-partial property, but fields which comply with that may not be conservative, so there's a lot of tests that are mostly to eliminate whether it is not conservative. And now we're going to move on to discussing integrals. So there's two types of line integrals, scalar and vector, and it depends on the type of field that is being calculated over. Scalar line integrals are integrals calculated over scalar fields and are found as f of x, y, and sometimes z, depending on how many variables, parameterized by one variable, which is usually t, and then integrated over ds, and that more specifically is the magnitude of r prime of t, so the magnitude of the derivative of our parameterization dt. If the integration function is 1 ds, or the only thing we're integrating over is the magnitude of the derivative of the parameterization with respect to t, then the integral calculates the arc length of our function. We can remember from Calc 1 that arc length is the square root of each component of the partial squared added together, and that is the magnitude of the derivative. And then the scalar line integral also calculates the change in arc length, which is proportionate to the change in the domain scaled by ds for a function. So this basically means it's the arc length scaled by ds for a function that does not have a value of 1. Additionally, this would be visually or geometrically represented as the scalar line integral would be the space above the parameterization but below the curve of the function. So the surface area under the curve. And vectors are always normal to the curve because, again, they are the parameterization and the derivative of the parameterization. The direction of a scalar line integral doesn't matter because they will always be equal. And now we're going to talk about vector line integrals, which calculate the amount of work a vector field does on a particle following the parameterized curve. And vector line integrals are calculated by dotting the parameterized big F gradient field with the tangent, which again is going to be the derivative of the parameter divided by the magnitude of the derivative, aka the derivative of the parameter dotted with our gradient field F. Now, the orientation and the parameterization of a vector line integral curve matter. For example, if you're walking uphill, the force acting on you is going to be different than if you're walking downhill. And vector line integrals can be calculated on a piecewise smooth curve, basically meaning that as long as you're never calculating an overlapping region and the bounds are set up so there's no holes or discontinuities, then you can still calculate a vector line curve. If you're calculating a conservative vector field line integral, where the field contains the whole curve, path independence applies, and path independence basically just means that it's kind of a different version of the fundamental theorem of calculus, that something can be calculated by just its endpoints, only path independence says that it doesn't matter which path you take to get to these two endpoints, you can just follow these endpoints. And then again, for conservative vector fields, the line integrals are always going to be equal if the path is closed. Now, this is because it's got the same starting and endpoints, so you can go no distance and cover the same distance that if you went, say, 20 miles around. Flux integrals also calculate the amount of fluid. Flux integrals are another type of integral, and they calculate the amount of fluid flowing through the vector field over a unit of time, and that can be summarized into rate of flow. Flux integrals are actually calculated by dotting F, which is our parameterized vector field, with the normal vector n, and then integrating over ds as our region, which is equivalent to dotting f of r of t, again the parameterized vector field, with the unit normal vector and integrating over dt, or integrating by dt. Calculations can be further simplified by the knowledge that a vector field is normal to the tangent plane, let's add that in there, and therefore is the equivalent of negative q with respect to dx, remember q is associated with y, plus p with respect to dy as a normal vector is basically the tangent vector but rotated by 90 degrees. And the tangent vector is going to be p with respect to x plus q with respect to y. And so we are simply adjusting this by 90 degrees by applying a negative and swapping the p and the q. Now we can discuss the fundamental theorem of calculus extensions that we have observed here in Calc 3. Beginning with Green's theorem, which basically says that a double integral can be calculated over a region using only information about the boundary of the region when the region is a simple closed curve. That is an important distinction to note, that it only applies when the region is a simple closed curve. Basically, Green's theorem is a two-dimensional version of the fundamental theorem of calculus, as it connects a double integral into a line integral of the boundary of the function, whereas the fundamental theorem of calculus is connecting an integral over a region to the starting and ending points. So both of them pretty much reduce it by a dimension and simplify the way that we can solve. Next, we're going to talk about Stokes' theorem. Stokes' theorem basically states that the surface integral over the curl of a vector field, dotted with the unit normal vector with bounds of a surface with flat upward orientation, can be calculated as a line integral over the boundary that is a simple closed curve. Stokes' theorem is a generalized version of Green's theorem, with Green's being a circulation form of Stokes' theorem. And Stokes' theorem describes how calculating the flux integral over a region can be simplified by only solving for the integral over the boundary of the curve. Again, we have a flux integral or a multivariable integral being simplified by calculating it over the boundary, which connects to both Green's theorem and to the fundamental theorem of calculus, which is connecting the integral over a region to the starting and ending points. And finally, we're going to talk about Gauss's theorem, which is also known as the divergence theorem. The divergence theorem basically states that the triple integral over a solid region of the divergence of f, so we would be using dv as our integrating region, can be calculated by taking the double integral over a piecewise smooth closed curve of the vector field within the solid region, dotted with ds. So this relates the divergence calculated with a triple integral to the total flow across a surface's boundary, which is the flux, And that is the same way that the fundamental theorem of calculus relates the area under the curve / the integral to its endpoints. Again, it is basically taking something that would be a triple integral and reducing it to a double integral in the same way that the fundamental theorem of calculus takes a single integral and reduces it to its endpoints. Gauss's theorem is also just a higher dimensional version of Stokes and Green's theorem. So yeah, those are the main big theorems that are extensions of the fundamental theorem of calculus, and those are some of the key components and formulas from advanced multivariable calculus. Thank you.